Hello and welcome to this engineering illustrated video, and here I will explain why electrical power is transmitted at high voltage and why grid operators normally use high voltage and not low voltage. So let's have a little background by firstly introducing what power transmission is. So power transmission can be represented in this figure. Essentially, we have a power plant which generates electricity, and this electricity it needs to be sent to the end user, and the end user would be either houses, factories, or basically in any city, any load that requires electricity. So, in order for the power that is generated by the power plant to be sent to the load, it needs to go through a medium, a transmission medium called transmission lines. And these are huge electrical towers. They are basically, uh, they link between cities. They are mostly outside of the cities. And they are always rated at high voltages. So if we look in more details about the voltage, so when we generate the electricity from the power plant, normally it's between 11 to 25 kV, and what we call that is a medium voltage. Now, in order to get the high voltage that we need to transmit through the transmission lines, which is around 100 to 700 kV, depending on the distance, we use what's called a step-up transformer. And what this machine basically does, it steps up the voltage from 11 kV to 130. And when the electricity reaches its destination, it goes again to step it down through a step-down transformer. And this functions basically the opposite way of a step-up transformer. So why do we need all that? Basically, it's the main goal here is to minimize losses. And by increasing the voltage, we will see how minimizing losses will basically lead to a more efficient and cost effective design of a power grid. So let's go to the next step. Let's go and let's go see exactly. Let's talk about the current. Okay, let's get into the math. So we said we need a high voltage. Okay, and there is a relationship between electrical power, voltage, and current, and the power factor. Okay, this is basically a fundamental relationship in all power systems. And if we rewrite the equation in this way, where the current is equal to the real power divided by the voltage and the power factor, we can see an inverse relationship between the current and the voltage. So what does that mean? When the voltage increases, the current inversely decreases. It should decrease, mathematically speaking. So if you plug in any numbers, just purely mathematically speaking here, if you put a high voltage, you'll get a lower current. And oppositely, if you increase the current, you will get also a lower voltage. Okay, so let's keep that in mind and see how a lower current will lower our line losses. So what is a line loss? In every power system, power is transmitted, as we've discussed, through transmission lines. And these transmission lines, they are not 100% efficient in transmitting the electrical power. So they are metal conductors, basically large metal conductors that travel very large distances between cities, from the power plants to the end user. And over these large distances, there will be losses. So it's not 100%. It's not 100% like efficient when the electrical power is transmitted. So how do we represent this the line losses mathematically? We use the second equation, which is basically the power lost equals the current that travels through the conductor, the square of the current, times the resistance of that conductor in that transmission line. And as we can see, loss is proportional to the square of the current. So if we have a high current, we will have very high losses in the transmission line. So a very brief example here. Let's assume we have, so it says if the current is reduced to 1/10, then the loss becomes, so if you plug the 1/10 where the current is, it will, the power loss will be 1/100. So that's 100% loss. Okay, so that's a brief example. Let's look in greater details now. Let's do a numerical comparison. So what do we have here? Let's see. Let's do a practical example. Let's assume we have we have two transmission lines, two case scenarios. The first, and for both scenarios, we want to transmit 100 megawatt of electrical power. And let's assume both have a power factor of 0.95, and the resistance of those conductors in this transmission line, to keep things simple, let's assume they're 0.5, just to keep the math consistent. So in the first case, we are using a low voltage of 11 kilovolts. So basically, instead of 132 here, it'll be 11 kilovolts. And here, in the second case, we will have 220 kilovolts. Now, as we said, our focus is on the current. We want to reduce the current. So let's find out the current that is flowing through the transmission lines in both cases. So when we plug in the numbers, with the power being 100 megawatts and the voltage for each case, we will get a higher current flowing through the transmission line in the case that has a lower voltage. So we have 5,000 here and about 200 amps in the second case that has a high voltage. Now when we want to calculate the copper losses, we're going to use those currents. And as you can see, when we plug in the number again, the same formula that we saw previously. So for a three-phase system, 3 times the square of the current, which are these numbers, times R, the resistance. Notice how we obtain a higher power loss for this case, even though the voltage is lower. Whereas in here, basically less than 1 megawatt. So now to summarize, we've said that a lower voltage will lead to a higher current flowing through the transmission lines, whereas a lower one, a higher voltage will lead to a lower current. And this eventually leads to higher losses for this case and lower losses. And so in this case, we will see that the percent loss, so basically from the 100 megawatt of power that is transmitted to the transmission line, we will get a 45% loss, almost half of it. And whereas in this case, less than 1% is lost. So using these numbers, from analyzing these numbers, we can clearly see that transmitting electrical power at a higher voltage through these transmission lines will lead to lower power being lost in the transmission process. So this so basically says high voltage reduces current and drastically reduces power loss in the transmission lines. So based on these numbers, we can see quite a few benefits of high voltage transmission. And as we've seen, and we compared in both cases, a lower current for the same power will lead to lower losses. Okay, because we said current is proportional to the power losses, so that will lead to lower losses, and that will lead to a higher efficiency. Because with lower losses, your power grid will become more efficient. And at the same time, because these transmission lines have metal conductors, because your current is being reduced, you don't need bigger conductors. So you will also reduce the conductor size. So you will use less copper, less aluminum, and this will also be more cost effective because it will lead to less cost for the construction. So these are the benefits. You'll also get less voltage drop, better voltage regulations, and a more economical large power systems. Now, generally in high voltage transmission, so there are basically the generation stage, which is basically at the power plant, and these are typically rated from 11 kV to 25 kV. And when that power is generated, we use a step up transformer. So this is the high voltage that is responsible for reducing the current. Okay, so that will be between 100 to 700 depending on the distance. So for long distances, the voltage will increase, and when the electrical power reaches the destination to the end user, we use a step down transformer to reduce the voltage again and then enter the distribution part. So this is the transmission part of the power grid, you could say, and the part where the electricity is consumed by the end user. For a three-phase system, it's 400 volt, and for a single, it's 230 volt based on the UK standard. So this is in the distribution part. And for extra high voltage, so they're used to move large blocks of power. Uh, these are for very, very long distances. Basically, they're used in large geographic areas like the US. Uh, and so depending on the need to transmit the power over distance, the right voltage will be used. But essentially, uh, regardless of the distance, the same principle applies. The higher the voltage, the lower the current, the current, and eventually the lower power losses. So another example, a visual example to see why should we not transmit at low voltage. So basically, it just summarizes the numbers that we've discussed. It will lead to a high current, and a high current will generate high power losses across the conductors that are used to in the transmission lines. You will for high current, eventually you will need bigger size conductors, so that is more cost for the material plus for the construction as well, and you'll also get more a higher voltage drop. So it's a cascading effect basically, where one thing leads to the other. Eventually it's not economical for very long distances. What we've discussed, let's understand it more with a simple analogy, just to get understand it from another dimension. So let's say we have two water tanks, and these two water tanks, they are the same capacity. They hold the same capacity of water, but they have different sizes for the outlet. So this has a small outlet, and this has a bigger outlet. So with the small outlet, we'll have a high pressure but with a lower flow rate. So a lower flow rate will generate less resistance in the water, whereas a bigger outlet that will allow water to gush out faster, it will cause more friction. And we can compare the high pressure with the voltage. So if we have, as we've seen, if we have a high voltage, the current will be less. And with the water analogy, if we increase the pressure of the water by reducing the by reducing the size of the outlet, we can deliver the same water at a far away distance, but with less friction or less current. Whereas here, if we use a bigger outlet, and the water will just gush out, it will not go far away, and it will cause a higher friction, and that higher friction will is can be compared to a higher current. And as we've discussed, a higher current will lead to higher power losses. So we can kind of compare uh, power system with this analogy in some form. So essentially, what our main focus is high voltage transmission is the backbone of modern power systems, and especially for transmission of electrical power through large distances, we always need to use high voltage. So that is the core concept. So to summarize, uh, the thing to keep in mind is the an economical and cost-effective power grid, especially for large geographical locations. It requires high voltage transmission, and that is needed to reduce current, which will eventually reduce losses and making the transmission more efficient, reliable, and economical. And as we've discussed, after transmission, it's stepped down for safe use. So yes, we do transmission the voltage through the transmission lines at high rated voltages, so over 100 kV. But let's say when it comes to the end user, they're not gonna use 100 kV, and that's where the step down transformer is used. To conclude, thank you for watching this video. I hope you enjoyed it. If you want to see more visual explanations for topics that are related to electrical engineering and power systems, please like and subscribe and share this video for more updates.